We're going to continue our discussion of the integral operators with surface integrals. So first we have to define the surface integral operator, and this is going to utilize a differential area vector that's perpendicular to the surface S. So this differential area vector is d sigma vector, and this is d sigma vector is in the direction of a unit vector normal to the surface. It has magnitude d sigma, such that the area of the differential element, which is the magnitude of d sigma vector, is basically ds. And with that, we can determine the surface area operator as the integral over the surface d sigma. The direction of the unit vector that's normal to the surface is determined by the closed path, which defines the surface boundaries and the right-hand rule. So for example, for this surface here, following the right-hand rule, our right-hand fingers curl in the direction following this path in the counterclockwise direction. You can see that the normal vector perpendicular to the surface points in plus I hat direction. That's also the direction of the d sigma vector. Whereas for this one, for this surface, if we follow this path, closed path, with our right hand, you can see that the d sigma vector perpendicular to the surface will be coming basically will be oriented towards us in this direction. So the direction of d sigma vector is found using the right-hand rule, where we have to determine the direction of the closed path with our right hand. That's in the counterclockwise direction. Okay, now since this d sigma is a vector, the surface integral operator is usually applied with a dot product. So application of the surface integral operator, surface integral d sigma dot product with a vector field. This gives us a scalar. That's one application. And in Cartesian coordinates, the d sigma vector can be written in terms of its components: d sigma I in EI hat direction, the unit vectors of the Cartesian axes, so that we have n hat dot EI hat positive will imply the d sigma I value, the component, is positive. If n hat dot product with EI hat is negative, this will imply that the component of the d sigma vector on the ith Cartesian axis will be negative. Okay. So with that, we can now write our dot product, the surface integral d sigma dot product with the vector field B is going to give us the surface integral d sigma I EI hat, the components of the differential area vector, dot product with VI EI hat, the components of our vector in Cartesian coordinates. So this will give us the surface integral d sigma I VI, which is going to be the scalar quantity we're looking for. Okay, it's also possible to act on a scalar field as well. So how can we do that? The surface integral d sigma acting on a scalar field phi will be basically using Cartesian coordinates EI hat. So this is going to give us a vector, closed surface integral d sigma I multiplied with our scalar field phi. So this is going to give us a vector if we use the surface integral operator this way. And it is also possible to act on a vector field as well. All right. And how do we do that? With a cross product. The surface integral d sigma cross product with vector v. This will give us, using our subscript summation notation, ek hat close the surface integral d sigma I vj epsilon I jk, and the end result is a vector for this application. Okay, so for surface integrals, we have seen that the surface integral operator is shown with an S on the integral sign, and it's the application of the d sigma, the differential area vector. The differential area vector is defined to be parallel to the unit vector that's normal to the surface of interest, and its magnitude is a differential area. The direction of this unit vector is determined by the closed path, which defines the surface boundaries, and the right-hand rule. So we follow the path with our right-hand rule. Our thumb points in the direction of n hat or d sigma. And since it's a vector, we can operate it with a dot product. So d sigma dot product with a vector v gives us a scalar. In Cartesian coordinates, it's d sigma I e I hat. So the components of the d sigma vector in Cartesian Cartesian axis. And if we find that d sigma dot so n hat dot I hat is e I hat is positive, that means d sigma I is going to be positive because the sigma vector is in n hat direction. So this is going to be the sigma I n hat, the sigma n hat. On the other hand, n hat dot e I hat is negative, is going to give us the sigma I is negative. So because the sigma is n hat the sigma. Okay. So now, having talked about the components of the differential area vector, we can substitute for the d sigma vector here d sigma I e I hat dot product with the vector v I e I hat in terms of these Cartesian components. So this gives us the surface integral d sigma I v I, which is a scalar. So this is giving us a scalar. On the other hand, it is possible to act on a scalar field to produce a vector. So this is directly writing the d sigma vector as e I hat d sigma I multiplied with the scalar field integrated over the surface. That gives us a vector. It's also possible to act on a vector field with the cross product, so that we have d sigma cross v surface integral using subscript summation notation. This is the surface integral d sigma I v sub j epsilon I j k e k hats. So this comes out as a vector. Now, what about volume integrals? So we can define the differential volume dv and the total volume with capital V, so that the volume integral is integral over the volume V dV. So this can act on a scalar field phi. So that's going to be the volume integral dV acting on the scalar field phi, which gives us obviously a scalar. So that's one possibility. And in Cartesian coordinates, we can write the differential volume dV as dx1, dx2, dx3. So for example, this would be dx, dy, dz. So that our volume integral dv acting on our scalar field phi would be integral over v dx1, dx2, dx3, which is our differential volume, acting on our scalar field, which is in general a function of x1, x2, and x3. It can also act on a vector field as well. So our volume integral dv, volume integral operator acting on our vector field v would give us the volume integral dx1, dx2, dx3 acting on our vector, which is going to produce a vector. Okay, so using the volume integral operator with integral v dv, dv is differential volume, which is dx1, dx2, dx3 in Cartesian coordinates. Acting on the scalar field phi, this will produce a scalar integral over v, dx1, dx2, dx3, or dx dy dz in Cartesian coordinates. Phi is a function of position, or acting on a vector field v directly, this will give us the volume integral dv, the vector field, which also can be a function of x1, x2, and x3, and the end result is a vector. All right, so we're done with the integral operators. So we have line integrals, we have surface integrals, and then we have volume integrals. And next we're going to talk about differential operators.